clearinghouse.
Right.
But it went in within like a week or so for me.
Did you?
It didn't sound like it was anything of horror if it got out, but
Took my leg off yesterday and all that.
I had no choice, I had to shoot it. All right, so I'm taking the copper pipe. So I'm just, it's an ordinary marker, nothing special about it, but it also happens to be a right size here. So just to give you some sense of how long it takes for something to fall through. To give you some sense of resistance that it might face, we sort of drop two of them at the same time. So roughly hitting about the same time. Not a lot of resistance inside. It is a smooth pipe inside here. And now take a magnet. Drop the magnet through. Let's make sure that they're roughly the same point. And I don't want it to actually hit the table. I've cracked some of these magnets already. Hopefully that's enough. All right, so the ends are roughly the same spot. There's a much clearer difference in how long it took for them to fall. So the question I'm ultimately leading to is, why?
Is there a magnetic field going around the magnets that store us in a spiral down the tube?
Why would what's spiraling down the tube?
The magnets are?
And what effect does that have?
Well, because it's getting pulled, the gravity is greater than the magnetic force. So it's gonna go down.
Oh, because of the magnetic force from the magnet to the copper pipe?
Yes,
Oh, let's take a look at that.
if it's not touching in the beginning.
Or we can even make it a smaller mass by taking a single one. Copper is not a magnetic material.
So then it has to have an electric field of some kind around it that's resisting the magnet.
Why would an electric field cause resistance in a magnet? Did you mean say magnetic field or?
Magnetic field, I'm sorry.
So there must be a magnetic field that's resisting the magnet?
I don't know, there's a field of some sort. That's
There's
created.
a field, there's grass on it.
Yeah. Right.
All right. Yes, part of what you've said is true. There's something opposing the magnet as it's falling. It's not being attracted to the sides,
Right.
in the sense of like the magnets against the board here. Anyone else want to speculate?
I mean, that, not to interrupt anyone that's thinking, but that would be the only thing to me that would cause any other restrictions from it falling down.
Okay.
What if you were to drop a single magnet versus all of the magnets?
So just one of these guys.
Yeah.
All right. These are just, most of these magnets came from, I think, Home Depot. Just ordinary, it's basically the strength of a kitchen magnet. Do you want to time it? Do you want it timed, or do you want to just sort of get a sense?
I was thinking like one magnet and the marker, just to,
Yeah.
like, I don't know if the forces of the magnet on other magnets.
Alright, so I think I can do that. So they're roughly, the bottom of that magnet is roughly the same spot as the bottom of this.
Okay.
I think for these particular magnets, the more magnets I have, the weight is increasing at a faster rate than the magnetic field is.
Right.
They're not ideal magnets where I put two together and I have a magnetic field twice as strong. I have better magnets over here. What do you think is gonna happen if I use the much better magnets?
Fall slower.
I think you'll get a good sense of it. I think we can agree that it's slower.
So, is the magnetic field being condensed inside of whatever?
Oh, well, all right,
Therefore, like,
Is it?
not really, but what are the implications if it's, so you're implying it's a stronger magnetic field?
right, and it's now acting upon itself with boundaries as opposed to acting on other things.
So it is exerting an external force on itself.
Right.
That would violate Newton's third law.
Okay.
So we're still holding Newton's third law as sacred.
So is the magnet's exerting a magnetic field, if I
Alright.
got the right term there this time, but it's acting upon the walls of it, so it kind of pushes and holds. It's not that it's acting against it, it's that the copper is acting back at it as like a, sort of like a mirror effect.
You're getting close.
Is it constricting?
Pardon?
Is it constricting the magnetic field that the magnet causes, which, does it have something to do with the polarization?
In a sense that the magnet is already polarized, there is a north and south pole. I mean, I would get the same effect dropping north in first as I would dropping south in first. But, I mean, there's some other things that we would not notice, differences between those two. I was making a point at some point to address something you said, and suddenly I realized I think I went off on a tangent there. So you were talking about constricting to the magnetic field? Is that similar to Gage's comment about condensing it?
Yeah, would it be the same if the rod was larger, if the hole was larger? And the magnet was the same size?
If it were larger,
The magnet was the same size, but the hole in the pipe was larger.
it would fall faster than it is. The effect would still, it should be slower than just free fall, but it will not be falling as slowly as the smaller.
Is it the fact that as it's falling, like as we were talking about before, magnetic fields can create electric fields, so as it's falling, the magnetic field is making an electrical field in the copper, which is then making a weaker magnetic field?
How? I feel like you're similar to what Joe said earlier when you mentioned electric field, and I wasn't quite sure if you meant electric field or magnetic field. I feel like you skipped a step.
Yeah, I was thinking there's an electric field in one of them and then a magnetic field in the other one. And they're both kind of counteracting on each other.
The electric field and the magnetic field are not going to counteract directly.
Is it like the magnetic field is inducing an electric field in the
And-
copper?
Which causes what?
With what we were saying, I guess a change in electric flux in the magnetic field?
Still skipping a step. All right, so again, so the magnetic field is falling. So for the sake of this, let's just assume north is down, south is up as it falls. It has a magnetic field coming out the north and into the south. And, we'll just do 2 layers there. It's supposed to be more symmetric than I've drawn it. All right, so as it falls, what can you tell me about the magnetic flux?
Turn this one. I guess that's, we see it's going straight down.
The magnetic.
Yeah, if I could drop it perfectly, it would fall straight down. In reality, it does, you know, you hear it clank up against the side every once in a while.
Yeah.
But in an ideal, perfect situation, if I dropped it, it would fall straight down and not touch the sides at all. I'm not that talented.
So the magnetic flux is kind of changing as it's going down, like wherever the center of the magnet is compared to the copper pipe, like that is always the same.
Okay, so if I look at this spot right here, the magnetic field, when it's way up here, the magnetic field is really weak, but obviously it gets stronger the closer we get to it. So when the magnet's here, it's much stronger. So we get this increase in the magnetic field, therefore increase in the magnetic flux through the surface.
If the tube was just a little bit smaller and it was the same size as the magnet, would it stay in the middle if there was no?
Oh, no, it would keep falling. The only way that you could get it to sort of hover is if we had something, if this were a superconducting pipe. In which case I'd have burned fingers at this point from how cold it'd have to be.
Gotcha.
Does it have anything to do with timing and the, like, stabilization of the magnetic field around the magnet?
Oh, as in it's causing the magnetic field within the magnet to disrupt?
Mm-mm.
Oh. Devon, you started down a line of thinking, and I feel like we got away from it. Did you want to pick it back up at this point?
Because I was thinking if it's gonna fall, it's gonna teeter, I guess like the magnetic flux is gonna teeter and tighter, so it's not gonna, I don't know.
Any bobbing back and forth of the magnet is probably weakening the overall effect. That I suspect it would be a much slower fall if we got a perfect drop.
Maybe if you used a ball.
Pardon?
A magnetic ball might be slower, because then you wouldn't have any sway.
That's possible.
Who's the guy that made the baby comment?
Faraday.
Is he the same guy that we were talking about the loop with the change in electric flux and the change of magnetic flux?
Yeah, it's same, Faraday's law, that same guy.
Okay.
You just dropping hints, or are you gonna run?
I'm trying to think it through,
Okay.
but I imagine it has something to do with that loop, I just don't know what.
As the magnetic flux is changing, is that what's generating an electric field with the equation we have on the board there?
It's creating an electric field, but there's another implication besides changing the electric field there.
Is it a?
Think in terms, instead of thinking of electric field, this is probably simpler, I think, in terms of thinking of the EMF. It creates an EMF. I mean, you can do it from an electric field that's created, yes, but I guess I'm projecting. To me, thinking of in terms of it's creating a voltage works better for me.
Hooked a multimeter up to it before you dropped it, would there be a voltage on the, that creates an electric flux, or electric, yeah.
I've never tried that, actually. I suspect it would be too small, but what the heck, let's find out.
We just try to follow it as it goes down, or?
Need another set of hands.
I figured just tape 2 probes to each side and see what happens, see if we get any reading that's not 0. It's got stuff up while, oh, actually, side quest might work better.
Might have to read in microvoltages.
The smallest volts.
Yeah, the multimeter is probably gonna, the multimeter is probably gonna flux or fluctuate just enough to counteract it.
For some reason, I have Sweet Caroline stuck in my head. I suppose one of you was singing it earlier.
I have a Red Sox fan, but I don't go around singing.
I thought a true Red Sox fan really didn't care what they sounded like.
That's a good point.
Oh, this metal's touching metal. Years ago, I was doing a demonstration where I was whipping a wire through the air, trying to generate something using the Earth's magnetic field, and I got some deflection on the ammeter, and I thought, all right, this is great. And then years later, I thought, I'm gonna do this one again. Zip, nothing. Still trying to figure out why it seemed to work that first time. Never worked since. One speculation is just happened to be in the right spot for the Earth's magnetic field the first time I tried it. Other speculation is a little more embarrassing, the fact that I could have just been, as I whipping the wire through the air, jiggling the meter, causing the needle to move that way.
Shouldn't that be higher as soon as where the ball drops into it? Like where it crosses the probes?
I figured I needed to give it some speed as it's falling,
Yeah.
and so if it's up too high, I don't think you're gonna get as big an effect. It's possible down at the bottom is the best one, but let's.
Is the magnet decelerating the entire time through?
If it's it starts at rest, so if it decelerates, what's it gonna do?
Yeah. Float.
I guess to add to that, is it falling at a constant speed while it's inside the pipe as opposed to accelerating?
Right.
I don't think it's constant, but I don't know for sure. I know that the other magnets I was dropping through definitely were falling at were speeding up as they fell.
Does it reach its terminal velocity faster than the marker?
I don't think terminal velocity is an issue here.
Okay.
So
I mean, it's probably smaller.
if we're
Oh.
creating voltage,
Yes.
would we also be creating a separate magnetic field
How?
from the copper pipe?
You're skipping the step. How is it creating a magnetic field from the copper pipe?
Magnet. There's two
Right,
parts?
the trouble with just saying a magnet, I can put the magnet there, I'm not creating
No.
a separate magnetic field right now. All right. Oh, that's right, I was going to change the rate of the sampling rate to, let's see if it can take 200. Oh, we can. Let's make it 1,000. All right. And for 18 seconds, that should be plenty of time. Because of the way it's taped right here, I'm gonna hold onto these, I'm gonna keep them pressed. And, all right. It got stuck. Oh.
The probes.
Oh, it,
Now it's stuck to the other one. All right, now hopefully it registered something but before it got stuck.
I didn't even think about that at all.
It's actually looking like something happened here. recognize there. Now, at what point did I drop it in? But I'm guessing that that's just noise there. That's as it approached, but let's see what happens if I zoom in on that. We're getting something there that looks like something that's happened.
It's like spiraling. Look, spiraling. Well, I can't see it from here.
Come on, you're young.
Oh, yeah, spiraling. Okay.
That could very well be from the spiral, but then it clearly stopped.
What's those dots? It's like I see dots on there. There's some points.
Oh, the circles?
Yeah.
Oh, that's something the LabQuest does, is they just put, I think there's, no, it's not a set pattern. Those are just points that they circling for whatever reason.
Cause that was, let's see. Let's put it there. Yeah, I was thinking that maybe those were points that I'd actually read, but I'm not sure why those are circled in particular.
All right, so back to what's going on. If a voltage is created, what's gonna happen?
Need an electric field.
Okay, they sort of go hand in hand, but, all right, so I have an electric field, what's gonna happen? A hint is, it would not work with a PVC pipe. I think at this point, we've pretty much established, I think Joe hit it early on, there's a secondary magnetic field, but what creates that magnetic field?
The movement of the electrons from the field that's created by the flux, by the electric flux.
Yeah, I think we can look at it that way. I was thinking from the magnetic flux creates a voltage which causes the current charges to move. I think there's a chicken and egg in here.
Backwards.
So as it falls, we get this change in the magnetic flux, which creates an EMF, which means there's a potential difference now. Charges want to move.